Temperature. It's something we feel every single day, right? But have you ever really stopped to think about what we're measuring? How do we put a number on something that's, well, basically invisible? Today, we're going to pull back the curtain and look at how we figured out how to capture a feeling, assign a number, and create a common language for hot and cold.
Okay, just think about this for a second. 77 degrees Fahrenheit, that's a beautiful day, right? Perfect for a walk in the park. But 77 degrees Celsius, that's not just a deadly fever, it's actually hotter than boiling water. So the number is exactly the same, but the meaning is worlds apart. It really proves that the number itself is pretty much useless unless you understand the scale it's on.
So how in the world did we even start trying to measure warmth? Well, early scientists had this really brilliant idea. Instead of trying to measure the feeling of heat, they realized they could measure what heat does to things around us. And this right here is the absolute key. So many things in nature change in a really predictable way when the temperature changes. A liquid expands, a metal's electrical resistance changes, some materials even change their color. And if that change is consistent, if it happens the exact same way every single time, then boom, you've just found yourself the basis for a thermometer. All right, so let's take that principle and see how it builds the tools we actually use. We're going to look at a few different kinds of thermometers, and each one uses a totally unique physical property to make that invisible feeling of heat visible. I'm sure you've seen this one a million times. It works on a really simple principle: thermal expansion. As that little bulb of alcohol at the bottom gets warmer, it expands. And it expands more than the glass tube it's in. Well, it's got to go somewhere, right? So it gets pushed up that tiny little channel. The higher the red line goes, the hotter it is. Simple as that. Now for a totally different approach. You've probably seen these on the side of a fish tank, or maybe as one of those forehead thermometers. Instead of using expansion, these use color. Each of those little squares has a special liquid crystal that's been designed to change color at a very, very specific temperature. It's kind of like having a whole row of tiny, colorful temperature alarms. And then there's this technology, which feels a little bit like magic, measuring temperature without even touching the object. It turns out that everything, you, me, the chair you're sitting on, everything gives off invisible infrared radiation. And the hotter something gets, the more radiation it emits. A pyrometer just reads that radiation from a distance. It's exactly how a firefighter can check for dangerous hotspots inside a wall without tearing it down. So we've got all these clever devices that work, but a measurement isn't all that useful if we can't agree on what the numbers mean. I mean, my 20 could be your 70. This is where temperature scales come into play. They give us that shared language we need to actually talk about heat. And the genius of creating a scale is just how simple the idea is. All you need are two fixed points, two temperatures that are always reliably the same no matter where you are. And what's the most reliable and available substance on the planet for this? Water, of course. Its freezing point and its boiling point became the universal anchors for our most common scales. And here you can see the core difference. Anders Celsius decided to set the freezing point of water to a nice, clean 0, and the boiling point to an even 100. Super logical. Daniel Fahrenheit, on the other hand, set those exact same physical points at 32 and 212. It's important to remember, both scales are measuring the exact same events, water turning to ice and water turning to steam. They're just using a different set of numbers to label them.
So what does this mean for the size of one single degree? Well, since Fahrenheit squeezes 180 degrees into the same physical range that Celsius covers in just 100, each Celsius degree represents a bigger jump in temperature. How much bigger? About 1.8 times bigger. This is actually why some people feel Fahrenheit is more precise for talking about the weather. You have more little steps to describe how the air feels. And it's the absolute reason you can't just add or subtract a number to convert between them. The very size of the units is different.
Okay, so we have Celsius and Fahrenheit for our daily lives. But science, it likes to ask bigger questions. Not just how hot is it, but what's the hottest something can be? And maybe even more interesting, what's the coldest it can possibly get? And that question leads us to this incredible concept, absolute zero. At its most basic level, temperature is just a measure of motion, the kinetic energy of atoms and molecules. The hotter something is, the more those little particles jiggle and zip around. So what would happen if you could just make them all stop? Well, you'd reach absolute zero. It's the bottom floor, the ultimate cold. Nothing can be colder. The Kelvin scale is built directly on this idea. Its 0 point isn't based on water freezing, its 0 point is absolute zero. That's why scientists use it. It's based on a fundamental property of the universe. And you'll notice we don't say degrees Kelvin, we just say Kelvin. It's an absolute measure. Now, if you look at the numbers for Kelvin, you'll see something really cool.
Water freezes at 273.15 K and boils at 373.15 K. What's the difference between those two numbers? Exactly 100. This means that the size of 1 Kelvin is exactly the same as the size of 1 degree Celsius, and that makes converting between them incredibly easy. So, now we have these 3 different languages we can use to talk about temperature. But what if we need to translate between them? Let's get practical for a minute and look at the simple math that connects them all. Here are the formulas you need. And you can see what we were just talking about. To get between Celsius and Fahrenheit, you have to multiply and add, because both the 0 point and the size of the degree are different. But look at Celsius and Kelvin. It's just simple addition or subtraction. That's because the size of the unit is exactly the same. All right, let's make this real with an example. In science, room temperature is often standardized as 25 degrees Celsius. So, what does that actually mean to someone who grew up using Fahrenheit? Let's run the numbers.
So we take our formula and we plug in 25 for TC. Now, 9 divided by 5 is 1.8. Then we multiply 1.8 by 25, which gives us 45. Finally, we add 32, and we get 77 degrees Fahrenheit. And would you look at that? We're right back to that pleasant picnic-perfect day we started with.
And what about converting to Kelvin? Oh, that's even easier. You just take your Celsius temperature, 25, and add 273.15. That gives you 298.15 K. It's that simple. It really shows you how closely linked those two scales are.
But there's actually one more layer to this whole thing. It turns out that even the freezing and boiling points of water can change just a tiny bit based on air pressure. So for ultimate, high-level precision, scientists needed an even better anchor point. And they found it. It's called the triple point of water, this one-of-a-kind, precise temperature and pressure where ice, liquid water, and steam can all exist at the exact same time. It's a true, unchanging constant of nature, and it's the modern foundation for the Kelvin scale.
Which kind of leaves us with one last thing to think about. We've seen scales that are based on water, and one that's based on the absolute 0 point of energy. If you were starting from scratch today, designing a brand new universal temperature scale, what universal constant would you choose to base it on?